Yes, and you guys should have all received an email from me with all of the stuff you've done so far and what you need on the final exam. And for the most part, you guys are all doing pretty great. So, and then it just says, you know, if you want this grade, just get this on the final. So, we will talk about the final exam today, and I guess I'll do a kind of a brief recap of the course. As soon as I can find my papers. Sorry. It's just... Okay, well, I'll just have to go off of my head then, which is, for the most part, good, except for today, apparently. Alright, okay, well, so let's just recap the different, well, I guess maybe before we get into the different statistical methods, maybe I'll just ask if you guys have any questions for me in general. Yes?
Is there any way we could get the homework back today to study from? Like
Yeah,
the
wait.
ones that we turned in today.
Oh, the ones that you turned in today. Okay, sure. I'll during the break, I'll just check off your names and then I'll give them back to you. So we'll do that. Okay. All right. Well, I guess maybe we'll talk a little bit some big picture stuff and go. Okay. So why do we study statistics? It's the last day before the final exam. Why did you guys bother taking this class other than saying it was a prereq and you're applying for a grad program or something? Well, huh?
There's another reason then?
There's another reason, yeah. Okay, well, what value should statistics add to your life then? How's that? If there is any. I'm teaching this class for nothing. Okay. Okay, so why do we study statistics? Okay, or why do people study statistics? Alright, so maybe you took the class because it's required or something. But why do we study statistics?
To give meaning to numbers.
Okay, yes. So we can look at data and draw meaning from them, right? We want to take data and be able to draw meaning. And basically, anytime we look at data, we're only looking at a sample. Okay, we don't have the means to study an entire population. We can't study everybody that we're possibly interested in. We can only study a sample. Okay, but I mean, in our dreams, we could study a population, but we can't. In reality, we can't. So we use statistics to be able to draw conclusions from a sample, and we hope to generalize these conclusions to the population. Okay? this is kind of the driving force behind everything that we've done, really, I guess. Okay, so in the beginning of the class, we learned things like the mean and the median and the standard deviation. Okay, we gave you these terms. Bar and whatever, okay. And these, this beginning chapter on, basically, these are all descriptive statistics. It was a way to introduce the language and terminology of statistics, because we throw around mean and median and standard deviation and all of this stuff. We use it quite a bit, so you just had to get an introduction to the terms, okay? So descriptive statistics, it almost served as a language of statistics. Okay. So what is the mean? The average, okay. And what is the average then?
The sum divided by the number of
Okay, so that's how we could calculate it, right? I mean, we add up all the numbers and we divide by however many we have. But I mean, why would the mean even be of interest to us?
It's our center value of the spread of our observation.
It tells us where the middle is, okay, or it describes the center, okay. Both the mean and the median describe our center, and the mean can be thought of as like the balancing point, okay. So it's a measure of center. It tells us about the center. And it can be thought of as the balance point. And then the median also tells us about the center, okay? And it tells us the literal middle point. Half are larger, half are smaller. These tell us kind of when we see a whole bunch of data, this tells us, about what center is, what a quote typical number might look like, okay? And of course these things only apply to numeric variables, right? We wouldn't have a mean and median for categorical. Okay, so these are all by the way numeric variables only. What about the standard deviation and the IQR? Bother talking about those things.
Well, the standard deviation is our distance between the expected distance between most of the values.
Okay. All right. So both of these, they tell us about the spread of our data. Okay. They tell us, how much variation is there. Okay. They're numeric variables, right? So are all of our numbers, are they similar to each other? Or are they pretty different from each other, okay? So these are measures of spread. Are the numbers similar? To each other? Or are they different? Of course they're different, but I guess drastically different. And the standard deviation can be thought of as, maybe the typical distance that our points are from the mean. the standard deviation is especially useful when we have something that follows the normal distribution, okay? Because in the case of the normal distribution, we know, what do we know? 68% are within one standard deviation of the mean, and 95% are within 2 standard deviations, and 99.7% are within 3 standard deviations of the mean. Okay, so we have the empirical rule, right? Okay, so that tells us, you know, about 2/3, whatever the standard deviation is, 2/3 of the data is within one standard deviation of the mean. About 95%. Oops. 2 standard deviations. Alright, so this also gives us an idea that, you know, nearly all of our data points, nearly all of them, are within 3 standard deviations of the mean. So it tells us, you know, the standard deviations give us an idea of the typical spread, typical distance that our points are from the mean, but it also tells us that nearly all of our points, especially for the normal model, is within 3 standard deviations. Sure, we'll get something that's 4 standard deviations away every now and then, but it's quite rare for something like that to happen. Okay, so anyway, that was what we did in the early chapters to kind of get us familiar with the language of statistics. But remember, all of this is because we want to make conclusions from our sample that we can generalize to our population. This is our driving motivation, okay? And so we took some detours and we learned about probability and all of those rules that we love, and the normal distribution. But after studying those things, we were able to understand sampling distributions, okay? And sampling distributions allowed us to see, whenever we take a random sample, what should this sample look like, okay? Know what, anytime we take a random sample, we don't know exactly what this sample is going to look like. But if we look at the mean of the sample, we have an idea of what it, quote, should look like. Or if we take a look at the proportion or things of categorical variables or whatever, we can study, you know, what this should look like, okay? And playing into this was the central limit theorem, okay? Basically telling us that sampling distributions end up following the normal distribution. That was kind of what the main point of that was, right? Well, sampling distributions for X bar followed up. because we understood, because we studied sampling distributions and we saw what our data, or what, anytime we take a sample, we had an idea of what the sample should, what it quote should look like, we were then able to use this knowledge to start making conclusions. And this was our first step into inference, okay? When we had confidence intervals and t-tests, we were using the ideas behind basically the essential limit theorem and sampling distributions. And we were using that to, I guess, draw a contrast between the actual data that we had and what it, quote, should look like. So, so understanding of sampling distributions. So, and the basic premise was we compared, our data to what a sample should look like. And almost always, our data is a little bit different from what it, quote, should look like, what we're expecting. And the question is the difference that we observed between our actual data and what we're expecting, is that difference significant? Or could that difference just be a result of random chance? Almost always. Different, a little, or a lot different. What we might expect. And to decide whether it was significant or not, whether it could just be a result of random chance, we had to look at basically the standard deviation of our sampling distribution, or our standard error. Okay, or for chi-square distributions, we divided it by the expected value, which oddly enough works out. So in many cases, compare our difference to some internal variation. Either a standard error or mean squared residuals, something like that. Right? Et cetera, et cetera. And that's kind of where we are, and we just learned a whole bunch of different methods on. So this is kind of the general idea. We're always looking at what our data looks like. We're comparing it or contrasting it to what we expected, and then we're asking, is this difference a big deal or not? And maybe the details of that process is a little bit different depending on what your variables look like. But that's the overall concept. Okay? So I passed out this flow chart of inference methods. It talks about, well, which inference method should we use? So the book actually has I guess a more complicated version of this in chapter 13 in one of the earlier pages. For that, there were a few a few statistical methods that are in the book that I did not cover in this class. Okay, a lot of the non-parametric ones and things like that. There are a few that I didn't get to cover, so that chart includes those, but this one's kind of just condensed down to the ones that I have covered. Okay, so if the response that we're looking at is numeric or is quantitative, then we've got a selection of. So we ask, is our response quantitative or categorical? Okay, so if it's quantitative, we've got certain methods that we use. Alright, and okay. So when we first started, we asked, okay, is the thing that we're using as a predictor, is our predictor categorical? Okay, so we have a categorical predictor. Okay, and the very first thing we learned was a t-test. Okay, that was, we have two different groups, two categories, and we're looking at the values in those in each of those groups, and we're comparing the means of each group. Okay, t-test. So we compare two groups. And basically, we're just taking the difference between x bars or y bars. And we're dividing it by the standard error. That was our t-statistic for the t-test. If we had, okay, so that was comparing the means of two groups, but this only applied when we had two groups and that they were independent. Okay, right? We also had a t-test if we had paired groups. Okay, paired groups, t-test for paired groups. So this chart kind of it does a better job of, I don't know, breaking out when you're using what. Okay, we have a t-test for paired data. And also that was two groups, but they're not independent. All of the data points are linked. Okay. And our t-statistic was the observed difference, d bar, divided by the standard error. And our standard error was s of d over the square root of n. And this one was the s1 squared plus over n1 plus s2 squared over n2. Okay, so we had t-test for paradigm. Okay, and then this was fine and dandy when we had two groups. And then if we had more than two groups, then we had to do ANOVA. Okay. And this one, basically, we had to compare what we were expecting from what we got. Okay, so we're comparing, you know, our data to what we got, and so that ended up being through the complicated calculation process. We are comparing our mean squares between groups. Okay, because according to our null hypothesis, all of the groups should look the same, should have the same value, and we're just looking at and we compared to the mean squares within it. Okay, and this gave us our F ratio. But all of these are really ratios, right? It's a ratio between the difference and the difference between things and kind of a measure of internal variation. So again, yeah, they look you know, the process is a little bit different, but the overall concept is still the same. Okay, and that's what we did when we had categorical predictors and a numeric response. Okay, and then this last week we just learned what do you have if you have a numeric or quantitative predictor, and a numeric response. Okay, so this is numeric or quantitative. And for that we used correlation and regression. And we just saw, you know, is there a relationship between the numeric predictor and the numeric response? Is there a relationship there or not? There's also, and we didn't get into the details, I mean, as to why, but there is also a test for significance, and it happens to be a t-test, okay? And also t-test for significance. Okay, for row. Okay. So just know the, I guess, calculating out that statistic and looking it up in the table, but as to the why it works out that way, that's a tougher question. Alright, so those were all, I think all of our methods that we learned for, oh, no, there's one more. Go back to these, okay? All of these, there is an underlying assumption of normality for the sampling distribution, okay? These all, even the ANOVA one really, there's an underlying normality assumption. Okay. And so we learned one method for when this normality assumption does not work, and that was the non-parametric test. the Wilcoxon-Mann-Whitney test. So if there's no underlying assumption, then you could use the non-parametric Wilcoxon-Mann-Whitney test, okay? And then so when do we use this? Basically, if you have major outliers that are an indication that this normality assumption doesn't apply, that would be a good time to use it. Okay, so use when major outliers and small groups and small samples. Because at some point, if your sample's huge, even if you've got outliers, the central limit theorem takes over with huge samples. Alright, and then on the other hand, we had if you had a categorical response. Okay, we only learned what to do with categorical predictors and categorical responses. Okay, categorical response, and all of our predictors are categorical. So. Categorical predictors, okay. So then if you have relationship of two categories. Okay, so categorical predictors. So here, if you want to see if there's a relationship between the categorical variables, then we would use the chi-square test for independence. Okay, and your degrees of freedom is number of rows minus 1 times the number of columns minus 1, right? In all of these things, the chi-squared statistic is equal to the sum of observed minus expected squared over expected. We just add this up for all of this. And actually, with the categorical response, if we had, I guess, preset proportions, okay, idealized proportions. Okay, we would do the chi-squared goodness of fit test. And our degrees of freedom is number of categories minus 1. Okay, and our chi-squared statistic is still observed minus expected squared over observed. Okay. Also, if we had idealized proportions and only 2 categories, we could do a confidence interval for P.
When you say idealized proportions, what is that?
If it's like when I roll the die, each face should show up 1/6 of the time. Okay, and so I roll a die, 100 times, and I want to, maybe each face doesn't show up exactly 1/6 of the time. Does my data indicate to me that these idealized proportions of 1/6 don't hold up? Okay, or maybe in your mind you've got the notion that 30% of flowers are red and 20% of flowers are blue and 50% of flowers are something else, okay? And you take a random sample and you're asking, do the proportions that I have hold up with the data? Okay, that's what we're doing here. Okay. And also, I guess if we have two categories, special case, we can also do a confidence interval for p tilde. Just that word. Okay. And we did not cover it, okay, and you don't need to know it. In case you ever run across the situation where you have a categorical response and a numeric predictor, you will use logistic regression.
Our numeric predictor is like.
So this would be like, if you go to the doctor and they discover some kind of tumor, okay, and they measure the diameter of the tumor or the width of the tumor. That would be a numeric predictor, and what they're trying to, the categorical response is this cancerous or is it not cancerous? Okay, is it benign? And so they might look at the size, and just based on, they're trying to use just the width of the tumor as a predictor here. They're saying, do we need to go through with surgery or not? Is this dangerous or not?
Are numeric predictors all like binomials, like?
No, a numeric predictor is basically a numeric response. I mean, a numeric variable. So, width, weight, something that you can measure, not a yes or no type of thing. So.
Okay, but I mean, is it like predicting like either like a success or a failure? Like you have cancer. Or you
Yeah,
don't have
it's
cancer?
predicting a success or failure. It could actually be extended to predict multiple categories. Usually two, but it can be extended to more than two. And we didn't cover that, okay? But it's out there. Okay. So you should know all of these different statistics methods, and yeah, you should know how to do each of them. So I think what I'm going to have on the test is there will be a section, just because it's hard to write a test and ask questions about which method are you supposed to use, and then have you go through with that method without revealing which method you were supposed to use. Okay, so so part of the test, I'm going to just describe kind of different scenarios, and based on the description of the scenario and the data that was collected, you need to identify which test is appropriate. Okay. So there will be the description, scenario, and data collected. Which test is, I'm looking at page 563 in your book. Okay. It says, researchers conducted a randomized, double-blind clinical trial in which some patients with schizophrenia were given the drug clozapine and others were given haloperidol. Okay. After 1 year, 61 of the 163 patients in the clozapine group showed clinically important improvement in symptoms compared to 51 out of the 159 in the other group. Okay, identify the type of statistical method that is appropriate for this data, but don't actually conduct the analysis. Alright. So don't shout it out all at once, but just think about what is the appropriate test for this one. Okay, we know.
What page is that?
Page 563 in the textbook. Alright, so 13.2.1, we are looking at two groups of patients. One got one drug and the other got a different drug, and then we are seeing whether they showed significant improvement or not in the clinical study. So, so what's the appropriate test here? A t-test? Okay. Okay, so what do we have a categorical or numeric response? A categorical response, okay? And it's just, did they show improvement, yes or no, okay? And our predictor is categorical, did they get this drug or that drug? So we've got, this would be a chi-squared test for independence. We want to know, is the proportions showing improvement, are they independent of the drug, or does there seem to be a connection to the drug? Okay, so this is a chi-squared test for independence.
You said, are they independent or?
Is there, basically we're asking, is there a connection between the drug used, okay, that's one, this is our predictor, and it's categorical. And our, and whether they showed improvement or not. So this is our response, and it's also categorical. Yes?
Could you explain why, what the difference again is like between two categories and relationship between two categorical variables?
Okay. So sometimes we just have a categorical response and there's no predictor. Okay, and we just want to know if our categorical response fits some idealized proportions, I guess. Okay, and that would be, you know, somebody says, oh, you know what, the Army has is 15% women and 85% men. Okay, and somebody says, oh, I don't know about that. Okay, so in that case, you have some idealized proportions in your head. In your mind, you think the Army is 15% women and 85% men. So you go out and you take a random sample from the Army, and maybe your random sample shows that you've got 16% women and 84% male. Okay, and this was after you sampled, you know, 200 soldiers. So in that case, does your data fit those idealized proportions? So in there's no predictor. There's no predictor. You're not trying to see if there's a relationship between a categorical variable and another categorical variable. You're just trying to see if those proportions hold up with the data. So, I guess it's different there. Okay? Alright, okay, and then 13.2.2 says do the actual analysis. Alright, well let's look at 13.2.3. Alright, and it says, okay, a biologist collected data on the height in inches and peak expiratory flow, a measure of how much air a person can expire measured in liters per minute, for 10 different women, and here are the data. And they're asking, is peak expiratory flow related to height? And you can see the data that was collected. So what kind of analysis is appropriate here?
ANOVA?
Correlation.
Okay, so what is our response? Yeah, our response is peak expiratory flow, and that's quantitative. Okay, so we've got different amounts of, I guess, how much air someone can breathe out. How do they measure that? Do you like go, or do you,
You blow into like a machine.
really?
It's in the physiology lab. It's
Yeah.
actually kind of cool.
Probably don't have too much big lungs or anything like that. Okay, so peak expiratory flow. They're like trumpet players. They're pretty amazing at this. Okay, and then we're looking at height. Okay, so PEF is numeric. And height is also numeric. Okay. Or at least the way they're measuring it, right? They're just measuring it straight up in these numbers. Height is in inches, so that's going to be numeric, and measured in liters per minute, that's also going to be numeric. So we're going to do correlation. To see if there's a relationship. And then you go through, you figure out the R, and you use that T statistic to see if it's significant or not.
So you want to see if height is correlated to.
Yeah, is there
Okay.
a correlation between height and peak expiratory flow? Yeah.
The X and Y. Right?
Yeah, X and Y, and you draw out those dots, and maybe it looks like that. And R equals 0.7. Is it? Okay. And then 13.2.4, they ask a question related to that. So 13.2.3, to do the actual analysis, you'd have to figure out correlation, and that would be kind of a pain to do by hand, right? With 10 people's numbers, you'd have to figure out the standard deviation and the z-score for everybody and multiply those. So that would be a little bit of a pain. But if I gave you like 4 or 5 data points, it's fair, right? Okay. All right. So yeah, learn. So know how to do correlation and correlation analysis for like maybe 4 or 5 data points. It's tough coming up with a good test that tests your knowledge, but also isn't so time-consuming or tedious. Alright, so 13.2.5, it says, a geneticist self-pollinated pink-flowered snapdragons and produced 97 progeny with the following colors: 22 red plants, 52 pink plants, and 23 white plants. The purpose of this experiment was to investigate a genetic model that states that the probabilities of red, pink, and white are 0.25, 0.5, and 0.25 respectively. Okay. Alright, so think about that. What type of statistical method should we use there? Yeah, so chi-square test, so we've got categorical response, and it's just the colors of the flower. But we don't have a predictor. We just have different proportions in our mind, right? 0.25 red, 0.50 pink, and 0.25 white. So, so this is going to be chi-squared.
And is this under the idealized proportions category?
Yeah, this
Okay.
would be idealized proportions.
Okay.
Yeah, so on your quiz, when there was the like the carnival game and you're spinning the wheel with the big prize or little prize, that was also idealized proportions, okay? Because ideally the wheel spins totally fair, and you know 1/12 of the time you get the big prize, and 2/12 of the time you get the little prize, and 9/12 you get no prize. Let's see, 13.2.7, okay. The effect of diet on heart disease has been widely studied. As part of this general area of investigation, researchers were interested in a short-term effect of diet on some kind of function, such as the effect of triglyceride level on the triglyceride level. And to study this, they designed an experiment in which 20 healthy subjects were given in random order a high-fat breakfast and a low-fat breakfast at 8 a.m. following a 12-hour fast on days 1 week apart from each other. Serum triglyceride levels were measured on each subject before each breakfast and again 4 hours after each breakfast. If you had access to all of the measurements in this experiment, how would you analyze the data? So we are measuring, I guess, triglyceride levels. So this is a numeric response. And what is our predictor here?
Categorical.
Yeah, it's categorical. It's whether we gave them a high fat or low fat breakfast. So this is categorical. And okay, so how should we analyze this data? Okay, so we only have 2 categories here, okay? But our data are dependent on the people. We have a before and after situation, okay? So we've got before and after. So before and after. So we would want to do a paired t-test. Okay. Someone could argue two-way ANOVA, two-way blocked ANOVA, okay? But we haven't really covered that, okay? A paired t-test would work for something like this, where we can compare the before and after. But, we could do a blocked two-way ANOVA design, but I think that's a little bit, we didn't quite cover that. 13.2.8, okay? We see, they measured, how many trees were in a wooded area, trees per 100 square meter plot. And they looked at square plots, round plots, and rectangular plots, and they wanted to know which type of plot had the most amount of trees. Okay, so we have our response is the number of trees. So that's numeric. And our predictor is shape of plot. And that's categorical. Okay, so we've got 3 categories. So what would we use? ANOVA. We've got a categorical predictor, numeric response. Okay. Well, so you'll have there will be a kind of a little section, maybe 5 questions or so, 4 or 5 questions, just on. I'll describe something kind of similar to this, and ask you what's the appropriate method to use. Okay.
Are there about 80 questions again?
Hmm?
About 80 questions again?
Maybe about maybe 60. I don't know. I'm still fine tuning some things. Well, should we run through some problems and go through the analysis or something, or I don't know what best to use our time here. Oh, you know what? Here, let me stop the video. There's something I do have to take care of.